Ever feel like you're drowning in information, like you just can't keep up with all the new stuff that comes out every day?
Right.
But you still want to, well, know what's going on, right?
Absolutely.
I mean,
Yeah.
you don't want to get left behind. That's what we do here on the Deep Dive. We bring you those core insights that you need to understand really complex topics fast.
We cut through the noise, get straight to the good stuff.
Today, we're tackling a big one, AI, artificial intelligence.
We've got a really detailed curriculum outline for this deep dive, a ton of information, so consider this your fast track to AI mastery.
Our mission today is to really unpack the fundamentals of AI. We're going to trace its evolution, get a grasp on the different types of AI, and of course, dive into the powerhouses behind it.
Machine learning, deep learning.
Exactly. We're also going to explore large language models like ChatGPT.
Which everyone's talking about.
Yeah, and we're going to see why Python is like the go-to language for all this.
The language of the AI revolution.
All right, so let's not waste any time. Let's get right into it. What exactly is artificial intelligence in a way that, makes sense?
Yeah, so at its core, AI is all about creating technologies that can perform tasks that, well, usually need human intelligence to do.
Okay.
So we're talking about things like perception, being able to see and interpret the world around us, language, data analysis, reasoning, problem solving, the ability to learn from experience and then make decisions based on what's been learned.
So it's a lot more than just, robots taking over the world like we see in the movie.
Right, yeah, absolutely. Well, those images are definitely captivating. A real-world example that's already changing things is OCR, optical character recognition.
I've heard of that.
Yeah. So that's the tech that lets you take a picture of a document, like a printed page, and then have it turned into editable text.
Hi.
That's AI in action. And it's making, information that was once trapped on paper accessible and usable for businesses and, well, everyone.
Yeah, that makes AI seem much more down to earth. So the aim is to create machines that can learn, reason, and, well, basically act like humans, at least in some ways.
Exactly. And to achieve that, AI pulls from so many different fields.
Right.
Obviously, you've got computer science at the foundation, but you also need data analytics, statistics,
Right.
hardware and software engineering, linguistics, even neuroscience, philosophy, and psychology play a role. It's really an interdisciplinary effort.
A bit of a melting pot.
It is. And in the business world, so much of the practical impact of AI comes down to machine learning and deep learning.
Right.
These are the real workhorses that allow AI systems to analyze huge amounts of data, identify trends that humans might miss, categorize information quickly and efficiently, understand and process language, offer personalized recommendations based on individual preferences.
Like when Netflix tells you what to watch next.
Right, and retrieve information quickly and accurately.
Okay, so the ultimate goal is to get these AI systems to do those really human things like learning, understanding, solving problems, making decisions, and maybe even being creative and acting independently.
Exactly. Think about the technology you use every day. Your phone, your computer. AI enables these devices to recognize objects in photos, to understand what you're saying when you talk to them,
Right.
to learn from the new information you give them, and even makes suggestions for things you might be interested in based on your past behavior.
That sounds a lot like the technology behind self-driving cars.
It is.
NASA actually has a good definition for AI, don't they?
Yeah. They define AI systems as those that can perform really complex tasks that typically require human intelligence, that learn from their experiences,
Yep.
that use data to improve their performance, that solve problems in a way that resembles human thinking, and that can act rationally to achieve goals, even in really complex and unpredictable situations.
So essentially it's about giving machines those cognitive skills that we usually associate with humans.
Exactly. The ability to learn new things, reason through problems, figure things out,
Right.
perceive the world around them, and understand and use language.
And all of this drives so many things, from online chatbots to deep analysis of data that would overwhelm a human.
Right. And what sets AI apart from older technologies is that it's data-driven. Instead of just following a set of rules, AI systems learn from the patterns they find in massive amounts of information. It's amazing to think that back in 1950, Alan Turing was already laying the groundwork for this by thinking about how machines could use information to solve problems in a human-like way.
That's pretty far-sighted.
It was.
So AI has a history that goes back a while. What were some of those key moments? How do we get to where we are today?
Well, the story really starts in the mid-20th century with pioneers like Alan Turing, of course, John McCarthy, Marvin Minsky, and Claude Shannon.
Okay.
These were some of the foundational thinkers who explored concepts like artificial neural networks, machine learning, and symbolic reasoning. They were laying the groundwork for what we have today.
It sounds like a real paradigm shift was starting to brew.
Definitely. But it hasn't been a smooth upward trajectory. There have been periods of, like, huge excitement and investment, followed by what are called AI winters.
Winters.
Yeah, times when funding dried up and progress seemed to stall. But then the field would see a resurgence, like with machine learning in the 1990s, or more recently, deep learning.
Like a cycle of boom and bust.
Kinda, yeah. One really big recent moment, though, was the public release of ChatGPT in 2022.
I remember that.
That really showcased just how far natural language processing had come.
It certainly grabbed everyone's attention.
It did. The idea of AI itself, though, isn't new at all, is it? Even ancient philosophers, like way back in 400 BC, were imagining the possibility of creating mechanical life, those, automatons.
Interesting. So the dream goes back centuries.
Yeah, and the official start of the field, at least as we know it, was in 1956 at the Dartmouth Conference. That's when John McCarthy coined the term artificial intelligence. And they set out some really ambitious goals. Well, to make machines that could use language, think abstractly, solve problems at a human level, and even improve themselves.
That's pretty ambitious for the 1950s.
Oh, yeah. But there was real progress in those early years. You had Arthur Samuel's Checkers program in '52. That was a landmark because it could actually learn to play better the more it played.
Okay.
Then there was the logic theorist in '55, which would replicate human problem solving. And in '66, you had Eliza, one of the first chatbots.
Like a very early precursor to ChatGPT.
Exactly.
So some big steps early on.
But they were. But then came the first AI winter in the mid-'70s. Funding dried up because, well, the field wasn't meeting those huge expectations that had been set. There was a report by Professor Sir James Lighthill that's really laid bare the gap between the promises and the actual achievements.
That must have been a tough time for AI researchers.
It was. But then in the '80s, there was a bit of a boom that was driven by the development of something called expert systems, which actually had some commercial success. But in the '90s, there was another downturn, even though research was continuing.
Another winter.
It seems like there's been this cyclical pattern.
It does.
But in the early 2000s, things really started to shift. Machine learning became more widely applicable, both in academia and in industry. This was thanks to more powerful computers, more data, and better mathematical techniques.
Like the pieces were finally falling into place.
Yeah. And not long after, deep learning emerged as a real game changer, surpassing traditional machine learning in some key areas. Then, in 2017, the introduction of the transformer architecture was pivotal. That led to a lot of the generative AI we're seeing now, like ChatGPT.
And to this huge surge in interest and investment.
Exactly. It feels like we're in a new boom period right now.
It certainly does. So within this world of AI, we often hear the terms narrow AI and general AI. What's the difference?
Right. So pretty much all the AI systems we have right now are examples of what's called artificial narrow intelligence, or ANI. Yeah. It's also sometimes referred to as weak AI. These systems are designed to perform very specific tasks. They're like, highly skilled specialists.
Okay.
Think about a search engine. It's fantastic at finding information, but it can't, say, write you a poem.
Right.
Facial recognition systems can identify people in photos, but they can't compose music. And speech recognition software transcribes what you say, but it can't design a building. These are all very useful tools, but they're limited in their scope.
They're good at what they do, but they can't do everything.
Exactly. And within their specific domain, they can often outperform humans. They can be incredibly fast, accurate, and they can process huge amounts of data that would overwhelm us.
Right.
This makes them really useful for automating things, improving efficiency, finding patterns in data, making predictions.
Yeah.
And they can work 247, no breaks needed.
Makes sense. What about general AI then?
So artificial general intelligence, or AGI, sometimes called strong AI, is the idea of a machine that has human-level intelligence across a wide range of tasks. It's not just a specialist. It's like a generalist. It could, in theory, understand, reason, learn, and apply knowledge to all sorts of problems, like a human mind.
A truly intelligent machine, not just a sophisticated tool.
Right. But that doesn't exist yet. It's a long-term research goal.
Okay.
And building on that idea is the concept of artificial superintelligence, or ASI. This is the idea that AI could actually surpass human intelligence in every way.
That sounds a bit scary.
It does raise a lot of questions, for sure. And there are other ways to classify AI, too. You have what are called purely reactive systems, which have no memory,
Yep.
limited memory systems, which can use past data,
Hmm.
and then the more theoretical theory of mind systems, which would be able to understand the thoughts and emotions of others.
Like reading people's minds.
Yeah, but that's still very much in the realm of science fiction. And then you have the idea of self-aware AI, which would have consciousness.
Oh.
And finally, you can categorize AI based on how it learns. You have rule-based AI, which follows predefined rules,
Right.
and learning-based AI, which learns from data.
And that's where machine learning comes in.
Exactly. Machine learning, or ML, is a key subset of AI. It's what enables computers to learn and improve from data without having to be explicitly programmed for every single situation.
So instead of giving a computer a set of instructions for every possible scenario,
Hmm.
you feed it a bunch of data and it figures out the instructions itself.
Exactly. The core idea is that you train algorithms on data, and they get better at making predictions or decisions as they process more data.
It's like learning by example rather than memorizing rules.
A good analogy.
So machine learning is about finding those hidden patterns in data and using them to predict what might happen in the future.
It is. While AI is the broader goal of creating intelligent machines, machine learning is a specific, highly effective way of achieving certain aspects of that goal.
So ML is one tool in the AI toolkit.
It's a powerful one.
And it's particularly good at recognizing patterns and improving its performance without having to be told exactly what to do in every situation.
Right. It analyzes data, makes predictions, and then adjusts its approach based on what it learns. You can think of it as a type of AI that excels at data analysis,
Yeah.
even without explicit step-by-step instructions.
Okay.
It really shines when you have a lot of historical data to work with.
Right.
It can uncover hidden connections and predict new relationships that you might not have even known existed.
So it's about discovering the unknown through data.
In many ways, yes. And a key figure in this field was Arthur Samuel. In 1959, he famously defined machine learning as the field of study that gives computers the ability to learn without being explicitly programmed.
That's a fundamental shift in how we think about software development.
It is, and another pioneer, Herbert Simon, emphasized that machine learning is all about improving performance through experience, much like how humans learn.
So how does this learning actually happen? What are the steps involved?
The basic process is you take a machine learning algorithm and train it on a set of data.
Okay.
The goal is to get the algorithm to recognize patterns or objects within that data so that it can then make accurate predictions when it sees new, similar data. It's like, imagine you want to teach a computer to recognize different types of fruit.
Okay.
You would show it thousands of pictures of apples, bananas, oranges, and so on.
Mm-hmm.
And the algorithm would learn to identify those different types of fruit based on the patterns it sees in those images.
So it's not just memorizing the pictures, it's learning what makes an apple and a banana.
Exactly. It analyzes the data and looks for those statistical relationships.
Okay.
And then it uses those relationships to make conclusions or predictions about new data.
So a typical machine learning project starts with collecting data, then preparing it, right?
Yes, that initial data processing stage is really crucial. It involves identifying and gathering the relevant data, cleaning it up, handling missing values, transforming it into a suitable format for the algorithm to work with.
Mhm.
And often it includes what's called feature engineering.
Future engineering.
Yeah, that's where you create, transform, or select the most informative variables from the raw data. You're basically trying to highlight the key characteristics that the model should focus on.
Like giving it the most relevant clues.
Exactly. Then comes the central phase, model development and deployment. This is where you take your prepared data, train your chosen model,
Okay.
fine-tune its parameters to get the best performance, and then test it on a separate data set to see how well it generalizes to new, unweaned data.
You want to make sure it can handle real-world situations it hasn't encountered before.
Right. And there's a growing field called machine learning operations, or MLOps.
MLOps.
It's all about making that whole process from development to deployment more efficient and scalable. Think of it like, setting up an automated pipeline for building, training, and releasing your models. But even after you've deployed your model, the work doesn't stop. You need to continuously monitor its performance, detect if its accuracy starts to decline, and have strategies to deal with those issues. Feedback from users is really valuable too, to see how well the model is performing in the real world.
So it's a constant cycle of learning, adapting, and improving.
It is. And the tasks that ML algorithms can perform are really diverse.
Okay.
You can have algorithms that predict numerical values, like sales figures.
Mm-hmm.
You can identify unusual events, like fraudulent transactions. You can discover natural groupings within data, like customer segments.
Okay.
And you can classify things into categories, like sorting emails into spam or not spam.
So different tools for different jobs. Now, we've talked about how machine learning learns from data, but there are different types of machine learning, right?
Yes, there are three main types: supervised learning, unsupervised learning, and reinforcement learning.
Okay.
And they're classified based on how they learn.
So let's start with supervised learning. It sounds like there's some kind of guidings involved.
Right. In supervised learning, you train algorithms using what's called labeled data. This means that for each input data point, you also provide the correct output, or the label. The algorithm's job is to learn a function that maps inputs to outputs, so it can then predict the output for new, unseen inputs. It's like learning with a teacher who gives you the answers to practice questions.
I see.
The two main types of problems tackled with supervised learning are classification and regression.
Okay.
In classification, the goal is to predict a category, like whether a customer is likely to churn or not.
Right.
And in regression, you're predicting a continuous value, like the price of a house.
Okay.
Some common algorithms used in supervised learning include linear regression, logistic regression, support vector machines, decision trees, and neural networks.
All right. So labeled data and predicting an outcome. What about unsupervised learning?
So in unsupervised learning, you work with unlabeled data. The algorithm only has the input data, and it has to try to find patterns and relationships on its own without knowing what the correct output should be.
So it's more exploratory, trying to discover hidden structures in the data?
Right. Typical tasks in unsupervised learning include clustering, anomaly detection, and dimensionality reduction.
What's dimensionality reduction?
It's about simplifying the data by reducing the number of variables while still preserving the most important information. Think of it like trying to find a more compact representation of the data without losing too much detail.
Okay.
Some algorithms used in unsupervised learning are k-means clustering, PCA, and certain types of neural networks.
And then there's reinforcement learning. That one always seems a bit different.
It is. In reinforcement learning, you have an agent that interacts with an environment.
An agent?
Yeah, think of it like a robot or a software program. And this agent takes actions in the environment and receives feedback in the form of rewards or penalties. Its goal is to learn a strategy or policy that maximizes its cumulative reward over time.
So it's learning through trial and error.
Exactly. A classic example is training a robot to navigate a maze. It gets rewarded when it moves closer to the exit and penalized when it hits its all.
So it learns the optimal path through the maze.
Right. Reinforcement learning is really useful in areas like robotics, where a robot might need to learn to perform a complex task in the real world, and in game AI, where the agent learns to play at a very high level.
Cool. We've talked about the types of machine learning, but where is it actually being used? Where is it making a difference?
Oh, machine learning has become essential in so many industries. It's everywhere.
Like where?
Well, in logistics, it's used to optimize shipping routes. In retail, it powers personalized recommendations and helps with inventory management. In manufacturing, it automates factory processes and improves quality control. And in security, it's crucial for threat detection.
So many applications.
Right. In businesses, it's used for fraud detection, to protect against security threats, to provide personalized customer service through chatbots, to transcribe and translate languages, and to analyze huge amounts of data to gain insights.
It's amazing how much of our daily lives are touched by machine learning without us even realizing it.
Absolutely. Think about things like facial recognition on your phone,
Yeah,
product recommendations online,
right.
email, scam filters, credit scoring, loan approvals. Even social media uses it for content moderation and targeted advertising.
It really is everywhere.
Other important applications are things like image recognition, like in Google Image Search, language translation services like Google Translate, personal assistants like Alexa and Siri, Gmail's email categorization,
Yeah.
even video game AI, and how search engines rank their results.
That's a lot of examples.
It is. There are different algorithms for different tasks, too.
Yeah.
For supervised learning, you have algorithms like linear regression, decision trees, random forests, support vector machines, gradient boosting. And for unsupervised learning, there are algorithms like k-means clustering and PCA.
Now, we've talked about machine learning, but then there's deep learning. Is that just a more advanced form of machine learning?
Yeah, in a way. Deep learning is a subset of machine learning that utilizes deep artificial neural networks to analyze and extract patterns from really complex data. You can think of it as the next evolution of ML.
Okay.
It's especially good at handling unstructured data like images, text, and audio. And it often achieves higher accuracy in tasks like image and speech recognition. A key feature of deep learning is that it can learn hierarchical representations of data, which means it can tackle really complex problems.
So what makes these neural networks deep?
The deep part refers to the number of layers in the network.
Okay.
Deep learning models can have hundreds or even thousands of layers between the input and output, which allows them to learn really intricate patterns.
So it's a matter of scale. More layers, more complexity, more power.
Exactly. And training these complex models often needs a lot of computing power. You usually need specialized hardware, like GPUs, to make it work.
Right.
But the payoff is that deep learning models can be incredibly accurate in tasks like image recognition, speech recognition, and natural language processing. They're able to find those really subtle relationships in the data that traditional machine learning methods might miss.
So deep learning is a real powerhouse.
It is. It's particularly well suited for handling unstructured data, like images, text, and audio. And often, it needs less human intervention in the process of preparing the data. With traditional machine learning, a lot of time is spent on what's called feature engineering.
Right, we talked about that.
Deep learning models can often learn the relevant features automatically, so that saves a lot of time and effort.
So less manual work and potentially better results. What's not to like?
Well, it does require a lot more data and computational power than traditional machine learning.
Great, there's a trade-off.
Yeah. But overall, deep learning is a significant step forward. Wow. It's almost like if you think of traditional machine learning as a surgical strike, very targeted and precise.
Yeah.
Deep learning is more like a missile strike, a feat of engineering.
Interesting analogy.
You're not just focusing on preparing the target, you're building a more powerful weapon. Or you could think of it like if AI is transportation, machine learning is cars, and deep learning is like electric cars.
More advanced.
More advanced, more sophisticated. It really is an evolution of machine learning.
So how do these deep neural networks work?
Well, at the heart of it all is this idea of artificial neural networks, which try to mimic the structure and function of the human brain.
Okay.
They're made up of interconnected computational units called neurons.
Artificial neurons,
And these neurons are organized into layers.
like in the brain.
Right. You typically have an input layer, one or more hidden layers, and an output layer.
And the information flows through these layers.
Exactly. Each neuron in one layer connects to other neurons in the layers before and after it.
Okay.
These connections have a certain strength, which is represented by a numerical value called a weight. And each neuron also has what's called a bias, which is like a threshold that determines when the neuron will become active.
So the weights and biases are the adjustable parameters that the network learns during training.
Precisely. The neurons themselves are the basic computational units.
Okay.
They receive input signals, perform a calculation, and then pass the result on to other neurons.
So they take in information, process it, and then pass it along.
Exactly. And the way they process information is determined by those weights and biases. During training, the network adjusts those values to improve its accuracy.
So it's like a network of interconnected processors, each one doing a small part of the overall computation?
It is. The input layer receives the initial data. The hidden layers perform those complex transformations, and the output layer produces the final result.
So for example, in an image recognition network,
The early layers might detect simple features like edges and corners. Then the next layers might combine those features into more complex shapes.
okay,
And then later layers might recognize entire objects based on those shapes.
it's like a hierarchy of feature detection.
Exactly. And one of the really powerful things about deep learning is that these networks can learn to extract those features automatically, directly from the raw data.
Right.
With traditional machine learning, you often need human experts to manually define those features.
So it's more automated.
It is. Deep learning models, especially CNNs, convolutional neural networks for images and RNNs, recurrent neural networks for sequential data like text, they can figure out those features on their own.
That's pretty impressive. So these networks are inspired by the human brain. How do they actually function to learn and make decisions?
Well, neural networks try to mimic how biological neurons work together to identify patterns and make decisions. They learn to model complex relationships by establishing connections between neurons. And those connections are constantly being adjusted during training.
Right.
And they learn from data. They're exposed to a huge number of examples, and they use that data to refine their internal parameters, those weights and biases, to minimize the difference between their predictions and the correct answers.
It's like a continuous feedback loop of learning and improvement.
It is. A key strength of neural networks is that they can generalize from the data they've seen. They can take what they've learned and apply it to new, unseen data.
So they're not just memorizing, they're understanding.
Right. They can make inferences from new data based on the patterns they've discovered.
That's pretty cool.
It is. And the way they learn is by generating an output, comparing it to the desired output, and then adjusting their internal parameters to reduce the error. It's a constant process of prediction, evaluation, and adjustment.
And we talked about activation functions. What role do they play in all of this?
Right. Activation functions are crucial because they introduce nonlinearity into the network.
Nonlinearity.
Yeah. Without them, a neural network would basically just be a series of linear operations, which wouldn't be very powerful.
Okay.
Most real-world data has nonlinear relationships, so you need those activation functions to capture that complexity.
Makes sense.
Some common activation functions are the sigmoid, ReLU, tan, and softmax. They all have different mathematical properties and are used in different situations.
Yeah.
You can think of them like decision points within a neuron.
Yeah.
They decide whether or not a neuron should be activated or fire based on the input it receives.
So they control the flow of information through the network?
Exactly. They're like those little gates between neurons that determine whether the signal should pass through.
And the learning process that adjusts the weights and biases, that's called backpropagation, right?
Yes. Backpropagation is the primary learning mechanism in most neural networks. The basic idea is that after the network makes a prediction, it compares its prediction to the actual correct answer. And based on the error, it adjusts its internal parameters, the weights, to do better next time.
So it's learning from its mistakes.
Right. It uses calculus to figure out how to adjust the weights to minimize the error. And there are different optimization algorithms that help to make that process more efficient and stable.
Okay, so that's how deep learning works. Now let's talk about large language models, or LLMs.
Right. These are a really significant development in AI. They're essentially AI programs that can understand and generate human language text.
Like ChatGPT.
Exactly. And they're trained on massive data sets of text, often containing billions of words.
That's a lot of text.
It is, and they use deep learning techniques, particularly a type of neural network architecture called a transformer model, to process all that data.
So they're learning the patterns and structures of human language on a massive scale.
Yes. And the result is that they can generate incredibly human-like text. They can answer your questions, summarize documents, translate languages, even write stories, poems, and code.
It's pretty amazing.
It is. And one of the things that makes LLMs so impressive is their flexibility. A single LLM can do all sorts of different language-based tasks.
Right.
It can translate between languages, write different kinds of creative content, answer your questions in a conversational way.
So they're not just good at one thing, they're good at many things.
Right.
And we're seeing more and more applications of LLMs in various fields.
Absolutely. They're being used to power chatbots, to provide more natural-sounding language translation, to generate creative content, to analyze data, even to write code.
What's the key technological innovation that makes LLMs so powerful? You mentioned the transformer architecture.
Yeah, the transformer architecture is really what's behind the success of these models. It's a specific type of neural network design that has revolutionized NLP. It uses a mechanism called self-attention, which allows the model to weigh the importance of different words in a sentence when it's processing that sentence. It
Self-attention.
allows the model to understand the context of a word much more effectively.
So it's not just looking at the words immediately around a given word, it's considering the whole sentence.
Exactly, and transformers can process the entire input sentence simultaneously, which makes them much faster and more efficient than older models that had to process text sequentially, word by word.
So they're parallel processors.
They are. A typical transformer-based LLM takes the input text, converts each word into a numerical representation called an embedding, passes that embedded,